Hello, everyone. So far, we've been building up the description of energy and mass balances individually to help kind of describe how we can um, balance a system. Now we're going to be trying to look at how we can balance these two ideas together. So, means it's time to return to our good old friend, flow diagrams. So let's go ahead and look at a very classic idea. So most industrial energy transfers are going to be looking at crossing two different streams to invoke a cooling line and say a heating line. So I may have uh, water, water and a product I need to heat on the other end. And so I'll just run them past each other and watch a certain amount of heat transfer in between the two. And there may be some additional heat coming in from outside the system. And again, using this idea of energy balance, the various inputs of energy for the system are going to be the actual heat I'm providing into the system and any enthalpy that's coming in with the molecules. And then the output is going to be, say, whatever I'm producing. So this may be something as simple as a high temperature product, or I may have actually had a reaction so that there may be some enthalpy change going in and out of the system. So if I'm dealing with a two-stream system, this becomes a little bit more complex because I've got two separate inputs and two separate outputs, which I can then condense to the heat being equal to the change in enthalpy of the first stream and the change in enthalpy of the second stream. Now, because of these kind of notations, and the fact that I never know the starting enthalpy of any given species, we're often going to want to set a basis that's going to be the most convenient for you. So the one that you're going to most commonly see me using is that the starting enthalpy of my inputs are generally going to be 0, and I'm going to be looking at how much they're increasing or decreasing along the way. So putting more of the focus away from this input-output notation to this change in enthalpy, encapsulating these two features together. So let's go ahead and kind of look at this in a little bit more detail. So one of the important things to note is that the energy being carried by the system is often going to be related to the mass of the system. So for example, if I'm looking at sensible heat, the change in enthalpy or the elevation of the enthalpy of my products is going to be related to how much of the system I'm pumping through, along with the temperature change. And so one of the things that's often going to end up happening is I may know something about the enthalpy change of one of my streams, and then what I'm going to try and figure out is how much mass I can heat or cool if I know, say, the heat capacity or temperature change of the second stream. So this is a little bit messy, but the major idea is that we can use these coupling of energy and mass to really help balance the designs of a real industrial cooling systems, which it turns out is where a lot of money is actually spent. So let's try and apply this to a real kind of system. So let's deal with with that rare case, a batch system. So let's say I've got an autoclave that's needed for the pasteurization of good old-fashioned Campbell's pea soup. So essentially, I can pasteurize a system by heating my soup up to pretty much boiling inside the container, 100 degrees C. So let's say I already have done that, and now I need to cool down the system with to a 40 degrees C. So this is actually a temperature which I can start to handle, and I'm going to do this by adding room temperature water till the water is the same temperature as the soup. So now here's the question, is how much water is going to be required to cool the soup? So we're going to assume a couple key features. First, we're going to assume adiabatic conditions. So no heat is entering or leaving from outside of my cooling chamber. And that each of my soups contains about 60 grams of metal with a heat capacity of 0.5 kilojoules per kilogram. and about 0.45 kilograms of pea soup, with the heat capacity of about 4.1, so slightly less of water, which has our good old-fashioned heat capacity of 4.186. So then we're going to be trying to figure out what kind of costs are going to be associated with this process, which is largely going to be trying to figure out how much water I need to end up using. So first thing for any good balance is going to be to diagram out the system and figuring out what we know and what we don't know. So I've got two streams which are going to be interacting. So stream one is going to be my cans of soup, which I'm going to set their starting enthalpy as 0, and their ending enthalpy is going to be essentially whatever is caused by having cooled down the soup. And similarly, my water starts with an enthalpy of 0, and its ending enthalpy is going to be due to the change in temperature or the sensible heat of the water. So let's go ahead and start by looking at that heat of the cans. So what we can do is break this into parts. So I have the metal and I have the soup component. So let's go ahead and start with the metal component. I've got 1,000 cans, which contain 0.06 kilograms of metal per can at a heat capacity of 0.5 kilojoules per kilogram and a temperature and a decrease in temperature of 60 degrees Celsius. Similarly, the cans also contain about 0.45 kilograms of soup at a heat capacity of 4.1, and again, the same decrease in temperature. So this means that the cans have, the metal has lost about 1.8 megajoules, and the soup itself lost about 110 megajoules of energy. So again, most of the energy is going into cooling down the soup itself and not the cans, for a net decrease in energy of 112 megajoules. Now that energy had to go somewhere, and it went into the water. So I know that the enthalpy of the water is going to be related to the mass of the water, the heat capacity of water, and the temperature change. Well, I know the heat capacity and the temperature change, but I don't know the mass. So I can go ahead and solve for everything but the mass. And then I know that the total heat has to be 0 because I've got an adiabatic system, which means that the two output energies, so the cans and the water, has to add up to 0, which means they're equal and opposite. So then I can set up the system to solve for the mass of water. And when I do this, it turns out that we need almost 1,800 kilograms of water to cool down those 1,000 cans. So it actually takes quite a bit of energy. And these are the general tricks that we're going to use for combining, helping use energy balances to solve mass balances. However, it's also worth noting that energy balances can also be treated as an extra known variable for any number of other complicated mass balance problems. So you may have a mass balance, you just simply don't have enough information to solve, and it turns out the missing piece is going to be the energy involved. So a good example of this is going to be, say, I've got a drying chamber at a chemical plant. So I produce a nice polycarbonate polymer that is actually very wet. It turns out that in the raw forms, a lot of these polymers are made in aqueous fashion. So it may have, say, about 55% moisture. So I go ahead and I put it in a dryer that consumes about 4,000 liters of natural gas at standard conditions. And that gas has about 800 kilojoules per mole, an efficiency of about 53%. So of the energy that that dryer produces, about 53% of it's going to go into drying my wet carbonate. So what we're going to be trying to figure out is how much water is going to be left over in that dried polymer, because it probably won't be perfectly dry. So we're going to assume the latent heat of water is 2.2 megajoules per kilogram, and we're going to be more or less ignoring sensible heat. Is it a good assumption? It's not bad. We're going to be missing some features by ignoring the temperature change of the water, but as we've seen previously, latent heat tends to be the dominant feature. So I've got a mass balance. So what's my first step to solving the problem? We diagram it out. And this will really help kind of sell what's happening. So I've got a wet polymer that comes in that's a little bit more water than it is polymer. Goes into the dryer. I end up getting a pure water stream and a stream that's much richer in my polycarbonate. So in order to do this, what I'm doing is I'm running a heater at 53% efficiency and passing some of that heat onto the dryer. So next step is going to really be trying to solve for this Q term, which we can then use to help figure out how much of the water ends up evaporating. So the first question is going to be, well, how many moles of natural gas are present? So for this, we're going to assume an ideal gas. So the moles is going to be related to PV over RT. Now, one of the things worth noting is that our pressure may be 1 bar, but our volume is actually present as a volume flow of liters per minute, which I'm going to end up converting into moles per hour. Feel free to go ahead and check the numbers. So what we end up doing is we're flowing through about 161 moles of natural gas per hour. So then how much heat is going to be released by this heater? So I've got this 161 moles of natural gas, which is going to produce 800 kilojoules per mole, but only 53% of that energy is going to actually make it to the dryer. So this ends up turning into about 68 kilojoules, 68 megajoules of energy per hour. So then I can translate this into how much water ends up being evaporated. So we can go ahead and turn that kilojoules into kilograms using the latent heat of water. So what we end up finding is that we're evaporating about 30.3 kilograms of water every hour. So we can use this to help solve our problem. So major approximations we're making is, again, we're ignoring latent heat, as well as assuming that we're working under an ideal gas system, which if we were dealing with standard pressure, actually isn't that bad. So let's go ahead and back this out to our more pictorial fashion, which we can help illustrate what we solved. Because if I'm evaporating 30.5 kilograms per hour of water, this means that I've got the remaining weight of that 60 kilograms, or 29.5 kilograms per hour, is actually going to be the dry polycarbonate. But then let's look at these numbers. I evaporated 30.5 of 33 kilograms of water, which means I've got about 2.5 kilograms of water left. And my original 27 kilograms of polycarbonate. So if we turn this into a weight percent, it turns out that I've got about 8.5 weight percent of water left in my quote unquote dry polymer. So one of the useful things that you may see with energy balance is that it's useful as a whole because we can also rearrange a problem to figure out how much heat needs to be provided, whether it's in terms of steam or a heater, but also helping identify what's present in product streams. So next time, we're going to be focusing in on the application of one of the most important unit operations in all of industrial chemistry. Next time, we're going to play with some distillation. Till then, take care.